Hello, scholars. Welcome. Professor Henkle here. Today, we are going to discuss waves, wave dynamics, wave features, types of waves, and all things oceanographic waves. Let's get into it. So, a lot of objectives here. We're going to do it. Instead of going through each one of these, let's talk about them in depth, in detail. So, waves, as we see here, are awesome and powerful and capture our attention. And when we usually think about waves, we think about surfers. Surfers catch waves in the surf zone. Here we see the biggest wave ever surfed by Sebastian Steutner in 2020. This wave was over 80 feet tall. Now notice that there are people here photographing, filming, and he was there to capture it. Because waves act in predictable and ways that we can understand. That is what we're getting into. What do we know about waves, and how can we predict where waves are going to occur? That's an actual application. So some things that are true. Waves begin as a disturbance of some kind. Mostly wind out at sea, but there's other types too. The energy of the disturbance gets propagated in the form of a wave. We're most familiar with waves that break on a shore or rock a boat at sea, and there are many other types of waves important to oceanography, which include internal, tidal, tsunamis. These are really big waves. Splash waves and atmospheric waves. Let's get into some wave basics. Here's a wave. It resembles the shape of a sine wave. Waves transfer energy through the water. And if we're to label some different areas of a wave, the peak of a wave is known as a crest. The bottom or the valley of a wave is known as a trough. The distance between two successive crests or two successive troughs is the wavelength, and the height between the difference between the crest and the trough is known as the wave height. All important for understanding waves. As waves travel, they have a speed. How fast are they going? And we can measure this speed by saying, well, how long is the wavelength? And what is the frequency? What's the frequency? The frequency of the radio, the frequency of the harmonics. Well, what exactly is that? It is the amount of waves that are traveling past a given point over a measure of time, usually in seconds. So it's the amount of waves per second. Now, the period, let's see, where is our little pointer here? The period is going to be the time that it takes for successive crests to pass a given point. So if this wave were traveling from this way to that way, the period would be from this crest to that crest. What's the time? The inverse of that is how many waves in that time. That is the frequency. Multiply the frequency times the wavelength, and you get the wave speed. Now, these are important dynamics for understanding the interaction and the development of waves at sea. When waves travel through ocean water, it is the wave that is traveling, and the particles undergo what is called circular orbital motion. Whereas the wave travels through, it travels up and forward on the front of the wave, down and backward on the back of the wave, up and forward the front, down and backward the back, up and forward the front, down and backward and back, so on and so forth. This circular orbital motion, mouthful, circular orbital motion, that is a mouthful, dissipates downward. So depending on the wavelength, the amount of water that will be affected by the wave is about 1/2 of that actual length. So the bigger the wave, the bigger the wavelength, the deeper the wave base is going to be. This is important, the wave base. equals the wavelength divided by 2. Because if the wave dissipates before interacting with the ocean floor, it's a deep water wave. If the ocean floor is high enough, it's a shallow water wave, and there are different characteristics to these waves. So let's go into them. Negligible water movement above half a wavelength. This is called a deep water wave, where the wave speed is the wavelength over the period, or the wavelength times the frequency. It is defined basically by waves in the ocean where the bottom of the ocean is really deep. As these waves are traveling, there's no interference of the ocean floor. When they get close, this is a surfer surfing the wave. When they get close to coastlines, like so, they become a shallow water wave where there's an interaction of the ocean floor with that wave. Now that interaction is going to cause waves to break. They become breakers in the surf zone near shore where the depth of that wave base intersects the ocean bottom. There's a place between transitional waves where there's characteristics of both the deep water wave out in the deep ocean and the shallow water wave on the shallow coastline, where it transitions from one type of wave to the other. So, okay, we've got wave basics, we've got wave anatomy, we've got different types of waves. This is all great. Love what's happening now. Where do waves come from? Well, they start out in the ocean, right? For wind waves, they begin as capillary waves, which are small ripples caused by the wind blowing over the surface. They're capillaries when the wavelength definition here, it's important, tied together, are 1.74 centimeters or less. When they become greater than 1.74 centimeters, they're now considered wind waves. Wind waves develop at sea through these 3 primary factors. This is a storm out in the ocean. That storm has wind. That wind has a speed and a duration over a given area. That area is called the fetch. Now, these 3 things together are going to determine how much wave energy is transferred from the wind into the ocean, which directly affects the wave height and the wavelength that will then move across the ocean. And when that wave energy is transferred to the coastline, develops into waves that break on the shore. So this is how waves are created, through storms out at sea. Now, as they're traveling across the sea, there's different levels of wave height that can be observed for deep water waves. And we have what's called the Beaufort wind scale that describes the appearance of the sea based on the characteristics of that wave height as created by the wind speed, duration, and area or fetch of the storm. It's all the way down from 0, calm, no waves, to 12, hurricane waves. 8 to 9 or 7 to 9 are gale force winds. So these are really strong. And then we got storm, violent storm, hurricane. These are determined. So we've got the description. We have the wind speed and the scale. Higher the wind speed, bigger the scale. So more intense waves happen with higher winds. Larger wavelengths and larger wave heights occur with faster winds because more energy is being transferred from the atmosphere into the ocean. This is, again, the air-sea dynamic, the interface of atmospheric and oceanic processes to create waves at sea. When a storm develops and it sends waves long distance away from where that actual storm happened or occurred, it can reach equilibrium conditions where the waves cannot grow any further, and they form what are known as swells. Uniform, symmetrical waves traveling outward from that storm area where the waves are all of equal wavelength. They have long crests, and they transport the energy long distances. These are what surfers love. Surfers love swells because there's a lot of them. The swells are coming in. You know, you can go spend hours in the water, and you will have these waves arriving in consistent, periodic sets. Wave interference. Not a lot of interference with these swells. One storm transporting waves long distance. But what we often see is different storms at sea interacting with each other, and they interfere with each other. And so this concept of interference is the interaction of waves. Here the red lines are two independent waves. When they're in phase with each other, they add to make bigger waves. That's constructive interference. Here, they're out of phase with each other, so the high crest, the crest on this wavelength is at the same as the trough, and the trough is the same as the crest. This cancels each other out. Destructive interference. Mixed interference is where you have waves of different frequency that combine to give wavelengths that are all over the board. So here we can see 3 incoming waves, lots of incoming waves to give you different types of waves in a mixed interference pattern. The waves are irregular and all over. Notice this very large wavelength. This is what's known as a rogue wave. So out at sea, rogue waves are when you have multiple storms interacting with each other, and because of the interference of the waves, you can get some extremely high wavelength waves. That creates a big wave at sea. These, on average, sink about 100 ships every single year because they're very hard to predict or to know or to even expect when they are coming. So rough seas with extremely large, massive, spontaneous, solitary ocean waves happen because of mixed interference. Okay, let's go to the surf zone. It's where surfers surf. Awesome, right? So the surf zone is where waves break near the shore. Here we can see deep water waves, deeper than L/2. Transitional waves, the wave starts to feel the bottom. As the wave gets closer, the amplitude increases and the wavelength decreases. So wave heights get bigger, wavelengths get shorter. When these waves get to the surf zone, they get to a certain place where they can't support themselves and they break. That's the surf that we think about. We could think about when a wave breaks as being the wave steepness, equal to or greater than 1/7. And the wave steepness is going to be the wave height over the wavelength. So here we go again. Wave height, wavelength. These factors determine deep water versus shallow water and when the wave is actually going to break instead of just being that smooth rolling surface transporting energy. This gives us a few main types of breakers that are really dependent on, well, what's the shape of the seafloor? Spilling breakers, gently sloped seafloor, waves expend energy over long distances and the water slides down over the front of the wave. Pretty calm. Spilling breakers. Here you can see the ocean floor is a little bit steeper as it approaches. These are called plunging breakers. These are the best for surfboarders, for surfers riding their surfboards. The energy is expended over a shorter distance, and the wave crest actually curls over on itself. This will create the barrels that surfers like to get in and hunker inside as the crest of that wave curls over them. It's breaking in the surf zone when the wave height over the wavelength is greater than or equal to 1/7. And then surging breakers, pretty steep ocean floor. This is where the wave crashes right onto the shore. Body surfers like this. This is not water that you would want to go swim in because you will get thrown around like you're in the middle of the washing machine. So here's that point again, Nazaré, Portugal. These are one of the locations where the biggest waves in the world occur. Now, it's going to occur when there is a storm way out at sea that sends swells of very long wavelengths to this area. Surfers ride gravity-operated water sleds, and this is a balance of the gravity and the buoyancy of the board where they position their board on the wave front, achieving speeds up to 25 miles per hour as they go down. Fascinating. Captivating. Wow, that's so cool. I couldn't imagine being that person riding that wave. This is a lot of water. Very heavy. Also very hazardous. People die big wave surfing every single year. So let's talk a little bit about waves and wave refraction. This is a property of waves. So as waves approach the shore, they start to feel the ocean bottom and they curl or they bend so that the wave crests are always nearly parallel to the shore, no matter what direction the incoming wave is traveling from. This gives us different speeds or different celerity of different parts of the wave through the different wave depths from the top of the wave to the ocean floor that allows for that bending to occur. That is why when you're standing on the shore, the waves always seem to be crashing directly at you. Waves are always crashing towards you. Water goes out, water comes in, water goes out. Because no matter the direction of the incoming wave, it's going to bend and arrive at you nearly parallel. Not only do waves refract so that they're always parallel to the shore, they also concentrate their energy on headlands with lower energy in bays. That's why the point is where surfers like, because it's the point break. It is the area of highest velocity. The waves concentrate on these points, which means that when the waves break, they're the biggest. And so that's where the surfers like to go. When a big swell comes in, the waves can travel all the way around through the bay. You'll get more gentle waves over here off the point, and then the biggest, strongest waves right along the point. This is known as a point break. We cannot talk about waves without discussing tsunamis. So tsunamis are not tidal waves. They are not influenced by the force of gravity, by the sun and the moon from the tides. Tsunamis, so the word tsunami translates to harbor wave because they are waves that can basically engulf an entire harbor. Now we know they are tectonically driven. It can be a landslide from the coast, which displaces a large amount of water, or it can be a convergent tectonic boundary that slips, releasing seismic energy into the water, creating waves that have extremely long wavelengths. So when they approach the shore, they go very, very far inland, up to 40 or 50 feet. Here we can see displacement, tectonic boundary. The wavelengths can be over 125 miles, which is incredibly long. In the deep ocean, they might go undetected. They're very fast. When they get close to the shore, they create some of the largest waves in the entire Earth that can be very damaging and extremely deadly, as we've seen from tsunamis in the past. Now, where do they occur? A lot around the Pacific Ring of Fire, where you have active convergent boundaries. If you've never taken geology, that might not make sense. But a convergent boundary is where you have forces of Earth that are moving in towards each other, creating compression. And when that compression builds up, there will be movement along a rupture surface, which is known as a fault, that releases that stored energy. That stored energy transfers into the ocean and travels as waves, just like wind waves do. Waves are how energy propagates through the oceans. So 2004, the Sunda megathrust fault slipped, creating a 9.2 magnitude earthquake off the coast of Sumatra. This was one of the most deadly tsunamis in recent history, killing about 230 to 300,000 people. It's a really big number because of how many people are unaccounted for. And it completely wiped out coastal areas, leaving almost nothing in its wake, affecting 11 different countries. So sad. Horrible loss of life. 2011, the Tohoku earthquake released a magnitude 9.0 earthquake right off the coast of Japan. Lots of people died, about 20,000 people died from the actual tsunami itself, but also the tsunami knocked out the power at the Fukushima Daiichi nuclear power plant, causing one of the reactors to overheat, melt down, releasing radioactive material into the environment, which we will still be studying for decades to come to understand the full effects of this tragedy. Please watch the video, Japanese Tsunami. So in conclusion, we covered a lot. Waves are an important part of ocean systems. It's how oceans transport energy, and it's how coastlines are shaped and eroded. These waves go very long distances. They interact with coastlines to produce different types of waves, different types of breakers, and these waves can be very deadly when large tsunamis occur on populated coastlines. So there it is. We've got wave basics, wave anatomy, wave development, wave classification, and extreme waves. Thank you so much for your attention. Have a wonderful day, and I'll see you in the next one.